So welcome everyone today to our CTA seminar. So today we have Dino Rossegger speaking about new examples of degrees of categoricity. So please go ahead.
Thank you. This is joint work with Barbara Chima. So let me start by introducing what it means for a structure to be computably categorical. So in this talk, we talk mainly about computable structures. So what I mean by computable structure is that there's like a uniform algorithm that lets us compute all the basic relations and functions on the structure. And we say a computable structure is decomputably categorical, where D is a Turing degree, if for every computable copy of A, there is a decomputable isomorphism between them. And if D is equal to 0, so if there's always a computable isomorphism, then we say that A is computably categorical. And this is a somewhat old research field which started in the 60s by work of Fröhlich and Shepardson, and independently by Yershoff in the back then Soviet Union. And what this notion lets us do, well, it lets us capture the algorithmic complexity of the structure, of the computable copies of a structure. Namely, if A is a decomputably categorical, then modulo D, all of the computable copies are computationally equivalent. So what do I mean by that? So here's an example. So for instance, using zero jump, if I give you 2 copies of the linear ordering on the natural numbers, then using zero jump, I can compute the successor relation. Like, I mean, I can always compute it on the standard copy, but on a non-standard copy, I might not be able to do that. But using zero jump, I can do it because successor relation is pi1 definable. So in particular, if I have zero jump, I can compute the successor relations and I can compute isomorphisms, because using successor relations, I can compute isomorphisms. And so if I have a relation R that I define on the natural numbers in some way that is invariant under isomorphism, then using zero jump, because I can compute, given, sorry, not only using zero jump, but I need zero jump and R to compute RA. So kind of like the relation R is like equivalent on all the copies of B, like if I know zero jump computationally. So computable categoricity recently, like more recently, has been a little bit refined, namely by starting degrees of categoricity. So let A again be a computable structure, then the categoricity spectrum of a structure A. So it's the set of all the degrees that compute isomorphisms between all computable copies of the structure. So here is like this big intersection, and so basically I take all the degrees that compute isomorphisms between all computable copies of the structure A. And then this categoricity spectrum of A might have a least element, and if it has a least element, then we call this least element the degree of categoricity of A. So this notion was introduced in 2010, and it has seen a lot of interest. And one of the main questions about degrees of categoricity is to characterize them. So in particular, we want to know which Turing degrees are degrees of categoricity, and we want to know which Turing degrees cannot be degrees of categoricity. So here are a few examples answering this type of questions partially. So in the first paper, they proved that every degree that is CE in and above 0 to the n for some natural number n is a degree of categoricity. Then this was improved by Chima, Franklin, and Shore in 2013, that every degree that is DCE, so like the difference between 2 CE sets in and above 0 to the alpha for any computable successor ordinal alpha is a degree of categoricity. Around the same time, Anderson and Chima found examples of degrees that are not degrees of categoricity. They showed that there is a sigma 2 degree D that is not the degree of categoricity. And I think I cannot see what I wrote here on the slide with this thing open. Yeah, which I should point out that this D, of course, is not above zero jump. Like otherwise, we would have contradiction with the results before. And also, like in this paper by Chima, Franklin, Shore, they showed that every degree of categoricity must be necessarily hyperarithmetic. So there's a lot of degrees which are not degrees of categoricity, but like the above example is one of a hyperarithmetic degree. And this was then continued. If you look at this Chima, Franklin, Shore example, so here the case for limit ordinals is omitted. And in 2018, Chima, Devo, Harrison, Trainer, and Mahmoud, they showed that if D is a degree CE in and above 0 to the alpha for alpha computable limit, this is also a degree of categoricity. And then also like Chima and Stephenson, also in 2018, give an example of a degree of categoricity that is not in any interval between two computable jumps. And recently, Chima and Ang were able to show that every delta 2 degree is a degree of categoricity. So this was announced already a couple of years ago, but the preprint appeared now. And they conjectured that in particular, every degree D in between 0 to the alpha and 0 to the alpha plus 1 in this interval for alpha bigger than 1 should also be a degree of categoricity. And if one looks at their construction, it's at least for any natural number, this should be quite easy to do using marker extensions. And I would think it's easily doable for all successor ordinals using known techniques. But for what if alpha is a limit ordinal, then at least the known techniques seem to have their limit, like where we cannot really. It seems to get too complicated to code limit ordinals in that sense. So it seems that the limit case in particular needs new techniques. Now in, I think like last year, Tenturetsky wrote a paper where he coded paths through trees into automorphism orbits of structures. And he was able to obtain some new examples related to computable categoricity. So he showed that there is a computable categorical structure that has high Scott rank. So let me just quickly explain what this means. So the Scott rank of the structure S, so that's the least alpha such that S has a sigma alpha plus 1 Scott sentence. So probably you know Scott's theorem, which says that every countable structure has a so-called Scott sentence in the infinitary logic L omega 1 omega that classifies this structure up to isomorphism. So like the models of this sentence are exactly the isomorphic structures. And so if you have a computable structure, then you can show that this alpha cannot be too high up. It's bounded by omega. So it's always less or equal omega 1 ck plus 1. And but there are computable structures where this alpha is actually omega 1 ck. And so what Turetsky showed is that there is a structure which is computable categorical, but like kind of its structural complexity, which is grasped by the notion of Scott rank, is like very high. So as far apart as it can be. And he also showed that there is a computable structure with computable dimension 2 that is not hyperarithmetically categorical. So what does it mean to have computable? What is the notion of computable dimension? It basically means that you have computable dimension alpha if there are alpha copies such that every other computable structure isomorphic to you is computably isomorphic to one of these alpha copies. But these alpha copies are not computably isomorphic. So what this means is, so if Turetsky's structure has computable dimension 2, so this means there's like two structures, computable structures, they're isomorphic. They're not even hyperarithmetically isomorphic, so like no hyperarithmetic degree can compute an isomorphism between them, but every other structure that is computable is isomorphic to one of the two. And yes, and so when one looks at the structure of at the proof of Turecki, what he did is he took computable trees and he showed that there is a computably categorical structure such that the automorphisms of the structure minus the identity automorphisms and the paths through T, through this tree, are Muchnik equivalent, modulo 0 double jump. So in particular, this so he also shows that like if the set of paths has cardinality 1, if there's only one path through the tree, if and only if there's only one automorphism. And then to obtain the first theorem, you can take a tree T such that the path through T is not a delta 1-1 set, for instance, like the descending sequences, infinite descending sequences through the Harrison ordering. Then you get like this structure ST that he constructs, which is computably categorical, but like there's no automorphism that is hyperarithmetically definable. Yeah, so the set of automorphisms is not hyperarithmetically definable, and this implies that it has high Scott rank. And then his second theorem is obtained basically by modifying the structure ST a little bit. And then, well, when I read this, I had this kind of dream. Well, okay, what happens if we can eliminate this 0 double jump? If we can eliminate this 0 double jump, then we could get results about degrees of categoricity, because then we could get, well, okay, like if D is a pi01 singleton, then there is a rigid structure with computable dimension 2 and degree of categoricity D. And basically just taking the second theorem of Turecki, we could get this just by using the right tree. Unfortunately, as it often is with dreams, like dreams usually stay dreams. And this cannot be the case. So it is well known that structures of finite computable dimension, so like that is not one, for example, Turecki's example is not very natural. Like they're always somehow artificially created. Like in natural classes of structures, you will not be able to find such examples. In particular, also Goncharov showed that if a structure is 0 jump categorical, then it must have dimension 1 or omega. So like in my dream, this case that like I get computable dimension 2 for any pi01 singleton is like, it's not going to happen because like 0 jump is a pi01 singleton, for instance. But also rigidity is a problem. Yamalev and Bashenov, they showed that there is a DCE degree that is not the degree of categoricity of any rigid structure, but every DCE degree contains a pi01 singleton. So this is also contradicts my example. Well, okay, then I thought, okay, well, but maybe if I still have a chance, what if D is a pi01 singleton and D is bigger than 0 jump? Well, the answer is unfortunately no. I still can't do it. Together with Barbara in this project, we showed that there is a degree D, which is between 0 jump and 0 double jump, that is not the degree of categoricity of a rigid structure. Our proof is basically takes Bashenov's and Yamalev's proof and combines it with a true stage construction. Let's quickly divert into that. To get a grasp of what Bashenov and Yamalev did, we have to consider a generalization of computable dimension, the spectral dimension. So we say a spectral dimension of a computable structure S is the least K, such that I have like a sequence of computable structures isomorphic to it that witness the full categoricity spectrum. So if you remember, the categoricity spectrum is defined to be like the intersection of all the degrees that compute isomorphisms between two copies, between all the two copies. And here I'm saying, well, is there a finite subset? Or like, is there a subset of that? And if it's finite, then the least subset is going to be this K. the least size of the subset is going to be this K, so it's a spectral dimension K. And it was also shown, like in the same paper by Bashenov, Kalimulin, and Yamalev, that if S is a rigid structure, then it has finite spectral dimension. Another observation is like, well, okay, if S is rigid, well, then clearly, then between any two copies of A, there can be exactly one isomorphism. So like basically every of these sets on the right here will contribute like one least degree. And so what Bashenov and Yamalev did, they used the finite Inge argument to construct a 2CE set D, such that for any two computable structures A, E, and BE, if there is a computable isomorphism between this A and B, that is Turing equivalent to this set D that's building, then they build a new computable structure NE, and an isomorphism F, which is not between NE and AE, which is not Turing below D. So D cannot be the degree of categoricity, right? Because this F basically tells you, okay, no, you cannot, D cannot compute an isomorphism between NE and AE. So this proof, as stated here, it only works for spectra dimension 1, because of course, otherwise I would have to consider joins of degrees. But it can be generalized to spectra dimension greater than 1. And so what we did is we just took their result and combined it with true stage techniques, their construction, to get a set D, which is between zero jump and zero double jump. So even like it is impossible to get for any pi 01 singleton, it's impossible for every pi 01 singleton greater than zero jump to get a rigid structure with computable dimension 2 with degree of categoricity this degree. So what is our main theorem now? Well, our main theorem is that, well, okay, we can do it, but we can do it only if D is bigger than zero double jump. So if D is greater or equal to zero double jump, and it contains a pi 01 singleton, then it is the degree of categoricity of a rigid structure of computable dimension 2. And what is maybe, so what I find pretty surprising is that actually we can do it for rigid structures for any pi 01 singleton bigger than zero double jump, because like, I mean, it's not so hard to see that, like, if I'm like above zero double jump and I'm like CE in above this degree, then and I'm seeing in above this degree, then I'm at the degree of categoricity of a rigid structure. But like after CE, the usual techniques break. Like for DCE, it's not the case anymore. So as a corollary, we get that every degree D in between the intervals 0 to the 2 plus alpha and 0 to the 2 plus alpha plus 1 for alpha computable ordinal is the degree of categoricity of a rigid structure with computable dimension 2. So in particular, if alpha is a limit ordinal, this works. So this is a considerable improvement to what was known before for limit ordinals. And what did we do? Well, what we did is we took this lemma, which I compiled for like all of these lemma that Turetsky proved, and eliminated the zero double jump on the left. So let T be a computable tree, then there is a computably categorical structure ST, such that the automorphisms are Muchnik equivalent to the path through the 3T plus zero double jump. And everything else is exactly the same as in Turetsky lemma. All we did is we basically took his construction and coded zero jump into the automorphisms. So I want to talk a little bit about this proof. The proof is an infinite injury construction, and there are 3 parts. So first is coding the paths through the tree into the automorphisms of the structure. The second part is making the structure computably categorical. So this is basically all the same as in Dan Turetsky's construction. And the third part part is coding zero double jump into these automorphisms, which is the new part. So what did then Turetsky do? So he took a tree T and decoded the path through the tree into a structure ST as follows. So for every element sigma, for every finite string sigma, he associated an infinite dimensional hypergraph with the elements of like hypergraph where the elements can be looked at as finite sets. And there's an edge labeled with I between two finite sets if the symmetric difference between f and g is I. So you can see here an example. So here is like a subset of this hypergraph of like all the sets, subsets of 1, 2, 3. So you can see, okay, so we have like this edge labeled by 2, and there's an edge between 2, 3, and 3, because the symmetric difference between 2, 3, and 3 is 2. And the same for, I don't know, 1 and 0, the symmetric difference is 1. So there's an edge, a 1 edge. So we get like this, we get this this cube here in this case. And we attach like this graph. I mean, of course, for all, like it's an infinite structure, contains all the finite sets. We attach this to this string sigma. To every string sigma, we attach a copy of this graph. And one of Turetsky's lemmas is that, well, if G is an automorphism of this hypergraph structure, it is an automorphism if and only if the automorphism acts by taking the symmetric difference between f and some fixed finite set h. So for instance, on the right, you can see how this automorphism acts by 3, by a singleton 3. Well, okay, what happens? Well, empty set, I have to take the symmetric difference with 3, so I swap it with 3. 2, 3 with 2, 1, 2, 3 with 1, 2, 1 with 1, 3, and so on. And you can see, like, just matching the colors up, that this is an automorphic structure. That this is an automorphism. Okay, so we know how the automorphisms, like if I give you a single sigma and I look at this hypergraph, I know like what are the automorphisms. But now I want, of course, like to code the path in some sense. And for that, we have a binary predicate P, which is defined by saying, well, okay, if I have like two tuples, like if I have f sigma and g tau, then I say that tau and tau is extending sigma by an element I. Then I associate f sigma with g tau if either I is not in the finite set f and the cardinality of g is even, or if I is in the finite set f and the cardinality of g is odd. So here's an example. On the right, you can see again an example how this P, for instance, would map the empty set of the node sigma to nodes in sigma followed by 1. So we have 1 is not in the empty set, so it will map the empty set to everywhere where g is even. So 0 is mapped to 2, 3, 1, 3, 1, 2. And 1, 2, which is even and contains 1, it is going to be mapped to all the odd sets. 1, 2, 3, 3, 1, 2. So now what happens if there's an automorphism G that acts, for instance, by 1, 2, by the symmetric difference with 1, 2? How can we deduce how G has to act on sigma 1? Well, of course, because for instance, it acts by 1, 2. So in what it needs to do, it needs to switch the empty set here with 1, 2 in sigma. But this means that it also needs to switch something here. It needs to swap even with odd elements. So in particular, if G acts on sigma non-trivially by delta H, then if I is in H, it needs to act non-trivially on sigma I and T. And our goal is that G can act by delta H, like non-trivially, can act non-trivially if and only if for every I in H, if I look at the tree, at the full tree above the node sigma I, the intersection between the full tree above the node sigma I and the path through my original tree is non-empty. And to achieve this, we need a last step. Namely, we have to kind of, so far we have laid out basically all of omega to the less omega, all the finite strings in my structure have attached these hypergraphs to it. So now what we need to do is we need to kind of somehow encode the tree T. And the tree T is encoded using these unary predicates, Sn, such that we say, okay, well, if a node sigma is in a tree T, then I will let Sn f sigma hold for all f and n. And if a node sigma is not in T, then I will let Sn f sigma hold for n, for all n, if and only if f is not equal to the empty set. So we let we let f it's if and only if f is equal to the empty set. So that's wrong here. So if f is not equal to the empty set, then there is an s, then there is an n such that S and f sigma does not hold. And so I could, like, at this stage where I'm not concerned about like the structure being computably categorical, I could just do this like with one relation and say, like, I don't know, S0 holds everywhere, or it only holds on the empty set. But we will need this to absorb some injury during while we make this structure computably categorical. So what we get from this is that the G can act by delta H for some non-trivially, if and only for every I in H, actually the extension from sigma by I can be extended to a path. So in particular, if the set of paths through the tree is equal to 1, then there is exactly one non-trivial automorphism, because there's only one node that always can be extended. And so how can we compute the automorphisms from the paths and vice versa? Well, given a path f, we can compute the automorphism that acts on an initial segment of f by just letting it act by the value of f on the length of this initial segment. And on the other hand, if I have an automorphism G, we can compute the path f. So the automorphism G, it might act on nodes by finite sets. It might not necessarily act always by singletons. But what I can do is basically, if I start with f0 and I take like the least element in the set f with which the automorphism acts from this set. This is my first element of the path. Then I look at this node, and I look at the least element of which the automorphism acts there, of the set the automorphism acts with there, and I continue like this by induction. So I can compute the path back. So this would achieve the first goal of the construction. Like, even we would not even have zero jump, double jump popping up anywhere. The problem is that this structure T is not computably categorical. So even though we have managed to code the tree, the path for the tree into the automorphisms, we cannot say anything interesting. So the next step would be to make T computably categorical. And this is a zero double jump. So this is a priority construction, infinite injury. It's like more or less like similar to the special component constructions that people do to get structures with computable dimension too. And the idea is that, well, if I list all the computable structures in the language of ST, and if I see that the IF computable structure is isomorphic, but not computably isomorphic to ST, then we destroy the isomorphism by modifying my ST during the construction. So this is a quite involved infinite injury construction. And what will be the result? The result will be that our ST is actually not that we get out of this construction. It's not representing the path through the tree T anymore, but it's going to instead represent paths through a tree Q, which is zero double jump isomorphic to the original tree T. So this is where like the zero double jump comes in the equivalence between the automorphisms and paths. And using these, we would get Turetsky's lemma. So like in the second step, we would get like this zero double jump here and here. So now to the third step, which is our contribution, and is actually not that difficult once you're familiar with then Turetsky's construction, is that we want to eliminate, if you remember, we want to eliminate the zero double jump here on the left side. So how do we do this? Well, we encode it. We encode zero double jump as initial segments into the initial segments of into the tree. So basically what we do is like, well, if sigma is a guy in our tree, like if sigma is a structure, if sigma is a string in our structure to which we have like this hypercube attached, and like Sn holds on all the sets F, then what we do is like, okay, then we want to enforce that like the ith bit of sigma is even if and only if I is infin in the set in the index set of finite C sets, and it's odd if I is not infin. So basically so we do this just by like adding a new strategy to the construction and interleaving it with the original strategies. Well, then we need to modify the strategies a bit, but it's not such a big modification. And using this, we get that actually, okay, now if I have a path, well, if I have a path, so if I have an automorphism of the structure ST, then this automorphism, it will act on the path, like on the extendable nodes of the tree, non-trivially, not on all of them, but on like some of them, at least on for the path. And basically from these extendable nodes, we can compute back zero double jump. So this is how we eliminate the zero double jump on the left. And then so the last step is, of course, to get like this. So now we have like this structure here, ST, it is computable, it's computably categorical, and like we have like the property of the automorphisms. So the last step would be to actually get a structure which has computable dimension 2 and is rigid if the set of paths has cardinality 1. So to get the desired structure, what we do is like, this is also exactly what Dan Turetsky did in his paper. Basically, we add 2 elements to the structure, ST, one element A even, A odd, and we take one copy and we say we connect using this P element, this P relation, we connect A even to the empty string, and like all elements of the hypergraph connected to the empty string, if and only if the cardinality of F is even, and we connect it we connect A odd to the empty string and all the odd sets related to the empty string. And then we add a constant C to the language, and in A we let C map to A even, and in B we let C map to A odd. So what happens? Well, area isomorphism between A and B must map C of A to C of B. So in particular, it needs to swap even elements with odd elements in the hypergraphs attached to 0. So it must act non-trivially on the hypergraph attached to 0. And then this of course extends for all the extendable nodes by the same argument as before. So in particular, area isomorphism between A and B computes a path for T. And if there's only one path, then A is rigid, right? Because there's only one automorphism, and like every isomorphism, it would induce an automorphism. So it, like in ST, it would induce an automorphism, and there's only one. And it is still computably categorical. What we how do we argue that? Well, you can just like take away A even and A odd and like look at the basic structure that lies between, like lies below. That's just ST or isomorphic to ST. ST is computably categorical, and then you just map up A even, A odd non-uniformly. So using this, we get like this main theorem that if D is a degree above zero double jump and it contains a pi01 singleton, then D is the degree of categoricity of a rigid structure with computable dimension 2. And looking at like which degrees contain pi01 singletons, we get that in particular every degree in the interval 0,2 plus alpha and 0,2 plus alpha plus 1 is a degree of categoricity of a rigid structure with computable dimension 2. So basically this confirms the conjecture of Gima and Ang, except that the zero jump case, that the interval between zero jump and zero double jump is still open. But using marker extensions, basically one can just use a lemma that Voggener, Kalimunin, and this should spell Kalimunin, I'm sorry, and Russell Miller proved. One can get the same result for the interval zero jump between zero jump and zero double jump. Yeah, thank you. So this is all I have prepared for today.
Yeah, many thanks for your nice talk. So are there any questions or remarks? I'm pretty sure someone will have a question. So just unmute yourself and ask your question if you have any.
So what do you see as your next project in this one? What seems feasible maybe is the way to the question.
I don't know. I think like, okay, so in my opinion, like, so this is still work in progress. We have not like completely written this up. I mean, you can just like easily like take some fancy pi01 singletons. I know, like, I think like Leo Harrington constructed in the 70s some cool pi01 singletons and get some cool results, but that's just like corollaries. Like as a new project for degrees of categoricity, I feel for like this existence, which degrees are degrees of categoricity and which degrees are not degrees of categoricity, I feel like we've answered all the feasible questions. I don't see any more feasible questions. What is a very interesting question is, and I haven't talked about this at all, is whether every degree of categoricity is a strong degree of categoricity. Yeah, this is still an open question. And I don't know, maybe one could use like this dense idea of like coding tree paths through trees and like reduce it somehow to a question about trees. So that would be something I would like. That would be the thing I would look into it now. Like, but
that would be interesting.
I haven't had any progress on that.
Thank you.
Okay, any other questions or remarks? So if that is not the case, then let's thank Dino again for his talk. Thank you very much.
Thank you for having me.
So, and thank you to the audience for joining us. So next week, Monday, November 8th, there will be a seminar talk by Cristobal Rogers in the Midwest Computability Seminar, which is co-hosted by us here. So I hope to see some of you next week again. I cannot create